Wait, wait. Hello? Okay, sure. Hello? Okay, should we start? Okay, so from this lecture, we are going to talk about probabilistic or statistic model, which is a powerful tool in artificial intelligence. So if you have a problem which has some uncertainty in modeling phenomena, you can just use this kind of statistical model to solve your problem. So this is the very first lecture of the statistical model. Today we are going to talk about the statistical inference. And a large portion of this lecture is just as same as the basic statistics and the probabilities. So you can just view this as a review of what you have already learned in statistics. Okay, so the first concept we want to talk about is statistical inference. So what is inference? Inference is a process of drawing conclusion by applying the knowledge you have to observation or hypothesis. And there are actually two types of inference. The first one is logic inference, which you use logic knowledge to make the conclusion. And another one is called statistical inference. In this case, your knowledge about the world has an uncertainty. Okay, so, and in this lecture, we're more interested in statistical inference. So now let's consider an example. If you find you cannot have access to internet, and you guess it's probably your network cable is broken. Okay, so is this a statistical inference or logic inference? Any idea? Why it's a logic inference?
Because you're not thinking about how often, like what the most regular code happening is.
It could be a statistical inference. Okay, because if you have no access to internet, there are multiple causes, right? And network cable is broken, this is just one causes. And you make such a conclusion is because probably you have a very bad network cable, right? So you think this is more likely to happen, but you cannot for sure, 100% for sure, this will cause your problem. So this could be a statistical inference. Okay, so then we will talk about the very basic stuff, that is the probability. So before I introduce the concept of probability, we need to first define a concept called sample space. Okay, so imagine you're rolling a die, there are probably 6 different outcomes. And you can just represent those, all the 6 outcomes in a set, like 1 to 6, right? And each element in this set is called a sample point. So this is an individual outcome of your random test. And then how to formally define a probability model is to associate those sample points with a measurement called probability. Okay, so probability should satisfy the following 2 properties. The first one is must be greater than 0 and less than 1, right? And another one is it must be normalized, which means the probability of all sample points must be summed to 1. Okay, so this is fairly straightforward. Okay, and you can further define an event. So event is a subset of your sample space. Let's say, for example, you can just define an event like rolling a die and obtaining less than 4, right? So this will, what will make this happen? This will correspond to 3 sample points. That is 1, 2, 3, right? And how to calculate the probability of this event? Okay, so you just make summation of all the sample points that is contained in this event or could trigger this event. Okay, so this is very easy. And atomic event means that event only contains 1 sample point. And the disjunction of 2 events, A and B, is defined as the event where the outcome satisfies either A or B. And similarly, you can define the conjunction of 2 events. So in this case, an event should satisfy both A and B. And okay, we can have the following examples. For example, like A is the event of rolling a die and obtaining less than 5. And then B is the event of rolling a die and obtaining less than 2. Okay, and then we can just define the disjunction, the conjunction of the event. And let's say if we calculate the conjunction of the 2 events, we can find only 2 sum points satisfy this event, contained in this event. Okay, and then this is the property of the probabilities. The first one is very easy. We have already talked about this. Is probability must be greater than 0 and less than 1. And if we say something is true in probabilistic sense, means the probability of true equals to 1 and the probability of false equals to 0. And the probability of a disjunction of 2 events could be further written by using the following equations. This is also very commonly used. And we can have an example here. So you have 2 events, A and B. And if we can first calculate the disjunction of the 2 probabilities. And then we can find that this probability can be also calculated by using the conjunction of the 2 events. Okay, so no problem so far, right? No problem? Okay, so I will go quickly for those parts. Okay, so this is a very tricky part, random variable. So a random variable, so if we formally speaking, random variable can be seen as a function. This is a little bit strange here. So this is a function mapping from your sample point to some range. So the range could be a real value or could be a Boolean value. Okay, let's say we define a random variable called odd. Okay, so the odd will take your sample point. Like let's say we have 1, 2, 6. This is our sample space. So we use this random variable as a mapping function. We take the sum point and it will return a binary decision, whether it's true or not. Okay, so if it's true, true or not, and then what is the probability of the random variable odd being true is basically the summation of all the probability of sample points that get true value of this function. So in generally speaking, it could be written by using this equation. Okay, so from this example, we can say that by using random variable, we can actually define an event. Very convenient to define an event. And usually, without confusion, we will simplify this probability Px, taking xi as Pxi. Okay, so this is a simplified representation of that. Oh, by the way, there is an important notation convention here. So if you are talking about a random variable, we usually use a capital letter. But when we talk about the value a random variable can take, we will usually use its lowercase. Okay, so now let's have a look at the types of random variables. So basically there can be three types of random variable. The first type of random variable is Boolean random variable, so it can be either true or false. Okay, another type of random variable is a discrete random variable. So for example, weather is can take like four different values, right? So we can think of weather as a discrete random variable, and obviously the values it can take must be mutually exclusive. And finally, we have continuous random variable. So in this case, the value a random variable can take is a continuous value. For example, like temperature, okay? So here I have a question. So what is the probability of a continuous variable taking an exact value? For example, we have temperature as a random variable. What is the probability of temperature equals to, let's say, 21 degrees? 0. Why it's 0?
Because it's not going to be exactly that value. It's infinite.
Yeah, that's true. So if you think about the possible range of a continuous variable, so then you can ask how many numbers are within that range. Because it's continuous, there are actually infinite number of them. And then we know the probability sum of them must equal to 1. But because there are infinite number of them, so each one is just a very tiny, approaching to 0. So what we usually do is we consider the probability of a continuous random variable is less than a given value. Okay, so do you have any problem with this? Okay, great. Okay, and we have already talked about this. Okay, then the probability distribution. Let's first consider the discrete random variable. So we know a discrete random variable can take a finite number of values, okay? And then probability of a discrete random variable taking those values could be called a distribution, or probability distribution. Okay, so here we have an example here. Let's first consider a Boolean random variable, the cavity. The cavity being true, let's say is 0, 1, and the cavity being false is 0.9. So we can just represent the distribution of this cavity, this is a random variable, in this way, right? So this is similar, we can just use this kind of representation to represent the distribution of a discrete random variable. And then we can see that this distribution of random variable are normalized, so the sum of them must equal to 1. And the discrete probability distribution is also called the probability mass function. Okay, so how about the continuous random variable? How can we define the distribution of continuous random variable? The trouble we have here is, just as you mentioned, the probability of a continuous random variable taking an exact value is equal to 0. Okay, so when we define the distribution of a continuous random variable, we need to start with the probability mass function. So this is the probability function we are interested. Okay, so we could see this as a function of x. X is the upper bound of this random variable. Okay, so this is a function about x. And then we can take the derivative of this one with respect to x. And then we get a measurement called the PDF, or probabilistic density function, of this continuous random variable. So it has a property like this. We can use the PDF of a continuous random variable to calculate its mass function. And then we can use this PDF to calculate an event. And we usually use px instead of p to represent the PDF. This is just to distinguish PDF from the probabilistic mass function. Okay. A very useful PDF is the, a very useful continuous random variable is called the uniform distributed random variable. Okay, so in this case, the probability density are same within a range, but be zero outside the range. Okay, so here we have an example. The random variable can have non-zero probability density within 18 and 26. But outside that range, it will be zero. Okay, for PDF, if we take an integer over all the range of your continuous random variable, you will have 1. So this is very easy to understand. It's still normalized. Okay, and then we can use this PDF to calculate an event. Okay, for example, what is the likelihood of this continuous random variable falling with this range? So why this equals to 0. Why is this equal to 1/4? Have any idea? Any idea? So you can just come up to write the equation here. Don't be shy. Okay, so to calculate this, you need to go back to this one, right? So this is just an integer over the range between 18 and 20, right? So basically, you calculate this integer, and this is just 2 times, right? Okay, then we can calculate the density of your PDF by using this equation. This is basically the definition of derivative, right? So we can just use this equation again to calculate this PDF. Okay, so another important concept is a Gaussian distribution. So this is still a commonly used distribution for continuous random variable. So in this case, your PDF is a function which is shown in this form. So its shape is just like a symmetry shape, and the center of this PDF is called mu, that is the mean value of this Gaussian distribution. And we have another parameters called the standard derivation, which controls the spread degree of this shape. Okay, so this is 3 examples of Gaussian distribution. Okay, so far we have talked about just a single random variable. Okay, and in most real-world case, we will encounter multiple random variables. So in this case, we will define a probability distribution called the joint probability distribution. So this is a distribution for a set of random variables. And we can just read it in this way, like px1 to xn. So what does this mean? This means the likelihood of the combination, right? So we're not just talking about the one random variable, we're talking about the combination of a set of random variables. For example, we can just define the joint probability of whether and cavity. Okay, so this is the two random variables. With the cavity, so the p whether being green and the cavity being true means that the probability that whether is raining and I have cavity. And then we can just define the joint probability by using a table. Okay, and we notice that the values in that table are summed to 1. So this is due to the normalization property of a probability. Okay, so this is called marginalization. This is very important concept for statistical inference. So so sometimes we're not interested in all the random variables we have. We're just interested in the joint distribution of a subset of the random variables. Then how to calculate the probability of them? We just sum over the value we are not interested in. Okay, so here we have example here. We have a joint distribution like this. So what is the probability of cavity being false? Okay, I will ask one gentleman or ladies to calculate here. Any volunteer? Okay. Sum over which one? Yeah. Yeah, that's right. So we just use the equation of marginalization. We can easily calculate this marginal distribution. Sometimes we call this as a marginal distribution. Okay. Another concept is called a conditional probability. So a conditional probability is a probability of an event given the observation of another event. So this could be written in this form. And for example, we have P cavity being true, condition on toothache being true. We have this probability equal to 0.8. So this means given the observation that a patient has toothache, the probability that she or he has cavity is 0.8. Right? And the conditional probability is formally defined in this way. So we can just calculate by using the ratio of two probabilities. Okay, and we can just rearrange the three terms and have this following relations. That is PAB. The joint distribution could be seen as a product of two terms. The first is conditional probability, and another one is sometimes we call the prior probability. This means we evaluate the likelihood of a random variable B without any observation. So this factorization, this is basically a factorization, is not unique. Okay, so we can just factorize it from A to B. This is to B to A, right? And then we have a chain rule. Chain rule is, so there we just have two random variables. So let's say if we have n random variables, we can just repeatedly, iteratively apply this rule. For example, we can first take the xn out of this combination and have this form, right? And then we can just again take xn minus 1 out. And then we can just repeat this process. Finally, we get this product equation. And then we can also combine the conditioning, combine the marginalization and the product rules to yield the condition rules. Okay, so this is still quite easy. Okay, and then we formally define the statistical inference as the computation of the as a computation from the observed evidence of probability for acquiring propositions. Okay, so the knowledge base we will use for statistical inference is actually the joint probability. Okay, and in the literature, there are actually two types of statistical inference. So when we talk about statistical inference, there are actually two types. The first one is called the Bayesian inference, and the second type is called maximum a posteriori inference, or MAP inference for short. So the outcome of the Bayesian inference is the probability of a random variable, the probability distribution of a random variable. But MAP is the value, the maximum likely, the most likely value a random variable can take. Okay, for example, let's say you find you have no access to internet, right? And you make a conclusion. This is because the network cable is broken. Okay, so is this a MAP inference or Bayesian inference? Any idea? So this is MAP inference. Okay, so in this case, the network cable is broken, is a random variable. It could be true or false, right? And you make a conclusion, this random variable is true. Okay, so this is just, you find the most likely value of that random variable. And if we do the Bayesian inference, we know the likelihood or the probability of it being true or false. Okay, I have one question. Why should we use Bayesian inference? What is the advantage of Bayesian inference? Any idea? Sorry?
If we have a lot of random variables instead of just one.
Well, for both inference, you make conclusion for one random variable. We just get different property of that random variable, right? So for MAP, we got the most likely value for that random variable. But for Bayesian inference, we got the probability distribution of that random variable. My question is, why should we care about the distribution? Yeah.
You can just pick any random variable, but if you use Bayes, then you can pick in a range. Does that make sense?
Yeah, it makes sense. So,
range where,
yeah.
where the other one doesn't, therefore you have more.
Yeah, so you got more information, and you can just sample from this distribution, right?
Yeah.
Okay. Any other idea? Okay, so let's just consider this with an example here. Suppose you feel uncomfortable and you go to a hospital and you did a lot of medical tests. And then finally the doctor said, unfortunately you have cancer. This is one outcome you can get. Another outcome is the doctor tells you you are likely to have cancer with a probability of 0.6. So which outcome you prefer? The second, right? So the first one just give you a decision without the uncertainty range, right? But for many real-world applications, you care about the uncertainty range. With this uncertainty range, you can understand how the system works, right? The confidence of the decision. And also, if you want to combine this test with other evidence, it's more convenient. So that's why we care about Bayesian inference. Okay, now let's have a look. Let's consider an example here. So the observation we have is the patient complains of toothache. Okay, and the query proposition is he has cavity. So what we are interested in is, given the observation, the patient has toothache, what is the likelihood of he has cavity? So the knowledge base we have is a joint distribution here. And in this joint distribution, we have another random variable called catch. This is basically, you can just imagine as a test method for a dentist. Okay, so the catch could take two values. It could be true or not. Okay, and then we have this table here. So this is like a joint distribution of 3 random variables. And we use this following notation in our calculation. So if the cavity being true, we can just simplify it as cavity with the first letter as a lowercase. Okay, so false, we just use leg cavity. Okay, this is similar for other random variables. Okay, so now we want to calculate this probability. So this means if we have toothache, what's the likelihood? What is the probability of having a cavity? So we could use this. What is this? This is just definition of conditional probability, right? And then for this one, what we have is a joint distribution of 3 random variables, right? But to calculate this one, we need to marginalize the unobserved or not interested random variable catch. Okay, for this one, we need to do the summation but over 2 random variables. So by doing so, we can just calculate this conditional probability. Okay, question, what is the probability that there is no cavity given the patient has toothache? Sorry? Why it's 0.4?
Because the initial probability was just the probability of a cavity given the toothache. This is still given the toothache, but this is just the cavity now. So it's
Yeah, that's right. That's right. So it's just 0.4. Okay, but if you want to do this one, if you want to use this formulation to calculate the 0.4 instead of 1 minus 0.6, you will find the denominator is actually shared by those 2 probabilities. So this means the conditional probability could be proportional to the joint distribution. And this could be very useful formulation to calculate do the inference. Okay, so let's say if you want to calculate this conditional probability, if we use the most straightforward one, we need to calculate this term and this term. The trouble is usually the denominator term. It involves 2 layers of summation, so it's not very easy to calculate. But we can just use this relation. We just define a normalized factor alpha here, right? And just write it this way. And this way we can just calculate, this is just a summation, right? We marginalize the unwanted random variables and do all the calculation work of this one. And then we know, as you mentioned, this should be sum to 1. So we just, no, okay, just maybe right here. So we know this relation, right? So we can easily calculate alpha here. And then we can just know the conditional probability. Okay, so this is a general rule for statistical inference. So basically, we have three types of random variable in a statistical inference. The first type is X. This is a query variable. That is the variable we're interested in. And we have E. This is just the infinite table, right? This is a joint probability. And then we have some observed random variable. That is the lower E, and Y is the remaining unobserved variable. Usually we call the hidden variables. So to make the inference, we need to make a summation over the latent variables we have, and we just take the value, take the observed value for the observed random variable, and then we can just calculate the conditional probability for the random variable we're interested in, and up to a scaling factor alpha. Okay, now let's consider an example here. Maybe we can do the last one. So we have the joint probability distribution like this. Calculate the following probabilities. So I'll give you 5 minutes and ask one volunteer to do it here. You can just come. Right? Don't be shy. You can just write down your equation there. Okay. It's just same as here. Okay, let's do it together. Just split this one. Oh, sorry. Okay, probably without the details of calculation, how about the general idea of calculus term? Any idea? How to do that? Yeah.
The conditional probability, like probability of toothache,
Yeah.
like with cavity, is the probability
Yeah.
divided by probability of cavity.
Yeah. Yeah. You can just calculate the numerator and the denominator, right? And then calculate the ratio, right? So this is just one way to do that. This is 100% correct. But perhaps a more convenient way is to calculate this term instead. So we can calculate this joint probability. So this means this is a random variable. So this could be either 1 or 0. And this should be 1, right? So this is the probability we're interested in, right? So this, I use just lowercase of the first letter. This means the catch is true, and toothache is true, right? And we can just calculate this one, right? And this one, to calculate this one, we need to marginalize the unwanted random variable. In this case, is catch. Oh, sorry, is cavity. Is this one, right? And this, we can find this value in the joint distribution table, right? Okay, and finally we will get two values from this. The first is when toothache equal to 1. And another case, this is true. Another case is toothache is false. Right, we got two values here, and we then normalize them to make the summation equals to 1. And then we can just pick the first one as our final results. This is another way to calculate this distribution, calculate this probability. Okay, so that's all for today's lecture. And then we have a tutorial session, right? Okay, so we will have more examples to come.
也不是啊，肯定是要参考这样。那否则可能零工巧网我还没有。
我都是上网，
哦，那还不是，应该是就是有些实现性看起来我还这样子。要是有些变化就是，你比如说它用结构体，然后之后我就把这个结构体全部改出来，然后之后比如说特别是 C 加加的话，因为它最查重最好的办法就是用 C 加加的到时候存在。第三步存在功能的话是不存在的。因为关键是没说完，存在的是咱们存在是同一个函数，然后它是变量的个数不一样，然后类型不一样，因为存在什么意思？就比如说是你可以定义两个整数变量相加 a 加 b， 写的就简单就加嘛。但是如果 a 和 b 的话，比如说它是就是 object， 它是 in class object， 就是你怎么两个类的中间相加，不是类的对象相加。这时候这个操作叫除在对象，就是它的加法的话，就是这个加号的并不再是简单的整数相加了。你比如说是它这个加法的话，是可以是变成也除在。加到字节码，或者是如果是开的话，它会变成汇编，变成汇编以后，它还有变量的地方。不是，你说那个你们那个时候他没办法查，因为 HDL 的话它是硬件，它之所以就是说其他代码。